So, in our very first kind of discussion about elimination, we brought up this idea of Zaitsev's rule. And Zaitsev's rule is kind of a guiding principle that we want to make our most stable product. And to make our most stable product, when we're thinking about double bonds or alkenes, you want the most substituted double bond, the most carbon stuff around that double bond. In the last video, though, when we were talking about E2 reactions, we added this kind of extra caveat that when you're doing your chemistry, if you're doing an E2 reaction, you need to have this anti-periplanar. And for a chair conformation, you need that trans-diaxial. You need a axial up and an axial down leaving group and hydrogen. And if you did not actually think about whether or not you had axial or equatorials, you would instinctively draw potentially a different product that wouldn't actually have an anti-periplanar nature. And while that seems like a potential violation of Zaitsev's rule, that reaction won't even happen in the first place because you don't actually have the right kind of orientation for an attack. And for a reaction to happen, you need to have a collision of sufficient energy with the right direction. And if we kind of go back to this last example, that HC proton is not in the right direction, so you're not able to actually get a reaction. So that's not really a violation of Zaitsev's rule. We can kind of see that almost as like an exception, though. Anti-periplanar is extremely important. There are a few other times when you can also get things that are maybe feel like they're an exception or they don't follow Zaitsev's rule. So I want to talk about a few examples other than this kind of anti-periplanar that we kind of got through in our last one. And our very first one is going to be a Hofmann elimination. Now, Hofmann eliminations are going to occur, and they're actually going to make the least stable product, the least substituted double bond. And the reason they're going to happen is because you have very big, bulky things. The main example that we're going to see a bunch is going to be a quaternary amine. So a quaternary amine is going to be a nitrogen that's going to have 4 carbon stuff, and with it having 4 bonds, when nitrogen typically wants 3, it's going to have a positive charge. This can also happen when you have very, very big, bulky bases. So if we think about this structure, and this right here, this quaternary amine, that is going to be your leaving group. And whenever you see a quaternary amine, a nitrogen with a positive charge, 4 bonds to it, that's going to be kind of a trigger in our head to be, oh, that's going to be a Hofmann elimination, and it's going to be the opposite of kind of Zaitsev's rule. So if we kind of think about Zaitsev's rule, and we have our different hydrogens here, we can call maybe HA on the left side and HB on the right side here. If we abstract our HA, and we had a double bond like right here where this green would be, that would end up being a di-substituted double bond because I would have 2 carbon stuff that would be connected to it. If instead I abstracted the HB, we would form a double bond over at the blue spot, and that would actually give a mono-substituted double bond. Because of the fact that we have either a really big bulky base or a really big bulky leaving group, there is actually a preference to only abstracting your HB. So you would actually get, in this case, abstracting an HB, making a less substituted double bond, and then your leaving group leaves. And especially, you'll also see heat almost always used in these reactions. That would give you then your product that would be the less substituted, as well as your trimethylamine and water. And this right here is kind of one of your exceptions, and that is going to be based on a few things. The first one is going to be on your quaternary amine. So your quaternary amine isn't that good of a leaving group, even though it does have a positive charge. They are a weak leaving group. and there's a lot of sterics. So we have a lot of big, bulky things, and those big, bulky things make it very difficult for your reaction to happen in the opposite direction of extracting your HA. So rule of thumb, if you see a big, bulky quaternary amine, that's going to be a trigger that's going to be a Hoffman elimination. And that is going to give you the non-Zaitsev product. The other interesting example is going to be based on conjugation. And this isn't really kind of like an exception to Zaitsev's rule, because Zaitsev's rule is really saying, let's make the most stable double bond. And if you can have a double bond that can do resonance, that's going to be more stable. So if you can add conjugation is just kind of another fancy way of saying resonance, that is going to be significantly more favored. So here, we're going to have an example where we have a benzene with a bunch of alkane stuff and an OTS. Reminder, OTS is a tosylate. So that is going to be an oxygen and then a sulfur that has 2 double bonds and then a like toluene structure. Tosylates are going to be good leaving groups. If you remember, we can install those on alcohols. Alcohols are bad leaving groups. You don't have alcohols that just leave, but you can do an SN2 reaction to turn an alcohol into a tosylate. And then that tosylate will then be a much better leaving group. So if this tosylate is my leaving group, and I think about my different locations that are exactly one away, I could consider a hydrogen here, which we would call HA, and then a hydrogen here, which I can call HB. And those would be the 2 possibilities that we could abstract from. Now let's go ahead and consider each of those. If I removed HA, I'm going to draw that same base structure, but all I'm going to do is I'm going to get rid of my tosylate, so that's going to be gone, and then I'm going to put a double bond between my HA and my tosylate. That would be if I did minus HA. Now, if I did minus HB, I would then get a double bond between my tosylate and my HB carbon. Now, if I think about my substitution between these two, the substitution on, we'll do it all in red. My substitution on this double bond is going to be di-substituted. I have exactly 2 carbon stuff around it. Over on my left side, if I remove HB, that is going to be tri-substituted. We have 3 carbon stuff. And normally we would say a tri-substituted is better than a di-substituted. However, in this case, our product on the left, our blue product, is conjugated. And conjugated meaning that I can do resonance. So I have a single double, single double, single double, single double. So all of those that are highlighted in yellow, you can do resonance through. So you can spread out that electrons all over. Where here, you actually have 2 single bonds. So that is a spacer. I have an sp3 hybridized carbon. So I cannot do any resonance between those. And because of that, this is going to make my product on the left, removing HA, my major product. So the vast majority of the time, we are going to follow Zaitsev's rule. We're going to try to make the most substituted double bond. However, there's a few kind of exceptions that we want to keep in our head. First off, can you actually abstract that proton? Because for E2, you need to make sure that you're anti-periplanar. If you have a big bulky group, especially like a quaternary amine, that's going to be an example of something that can do a Hoffman elimination. And that will actually make the less substituted double bond. And if you can do conjugation, if you can build up conjugation, that is going to be favored regardless of your substitution. So those are kind of like 3 kind of like checks to the kind of overarching theme of your Zaitsev. That's going to be something that's going to be super unique in your E2. In your E1, because of the fact that you don't need to worry about the traffic, a lot of those kind of things you don't need to worry about nearly as much. And that's going to be kind of a good point, I think, to stop for most of our elimination. We'll do a bunch more examples of thinking about what types of eliminations you can do and some exceptions in class.